if two adjacent characters in the string, that's what this means, are both vowels, so both of them are either A, E, I, or O, or U, then we have to determine if they're glottal stopped or H'd, i.e. check if they're the same or different. And we find the absolute difference using the ABS function. Because if, let's say, you are doing number of glottal stops minus number of H's, but the number of H's are greater than the number of glottal stops, we don't want a negative number, so we just use the ABS function, which is short for absolute. Okay. And if this difference in glottal stops and H's is greater than in the previous word, then we update the maximum value of the difference. So what do I mean by that? It's just right here. So RES. I'm not sure what that means. But essentially, we do this. Okay, at the end, we find out how many glottal stops there are, how many H's there are. We find the difference. And if this difference is greater than our previous maximum number, the previous maximum difference in another word, then we update our maximum difference in order to get the answer. One thing I saw in some people's code is that they had a for loop, and then inside the for loop they have an if statement, and that if statement essentially checks if the character is A, or if the character is E, or if the character is I, or O, or U. You don't actually have to do that for every single. You don't have to put every single possible vowel inside the if statement. What you can do is just have a set and input every vowel character into that set, and then check if the character you're looking at is inside the set. That's where you can see if it's a vowel or not. It looks much better when someone's looking at your code, and it'll probably make it easier to debug. Okay, question 5, Sudoku 2. I didn't actually do this question yet also. So let's just look at the prompt statement first. Okay. Now let's just read it. Wait. Potato was playing Sudoku and thought he found a solution. Help him check if his solution is valid. Given a 9x9 grid A, where each cell contains an integer between 1 and 9 inclusive. Specifically, cell at either okay. Verify if A satisfies the following conditions. For each row of A, the 9 cells in that row contain each integer from 1 to 9 exactly once. For each column, the same thing as well. And for each 9x9 square partition, they also have an integer from 1 to 9 exactly once. So what does that mean? It's essentially just normal Sudoku. For each row and each column, there can only be the numbers 1 through 9 happening exactly once. So we see here 1, 2, 3, 4, 5, 6, 7, 8, 9. We cannot have 1, 1, 3, 4, 5, 6, 7, 8, 9. And for each 9x9 square, 9x9 square means over here, this 1, 2, 3, these 3 rows are 9x9 square. Not these 3. Okay, it's not those. It's every 9x9 square, 3x3 square, to form a Sudoku board. If you're not sure on the rules, you can just Google the rules of Sudoku. Okay, so let's see, give me a second to just read through this. Okay, so as you can see in this input here, right? You look at this bottom right, 3x3 square. It has 6 appearing 3 times, 7 appears 2 times, 5 also appears 2 times, which means that it's invalid, so it doesn't work. So how would we solve this? How would we check if this Sudoku board given to us is valid? Okay, so firstly, we input the Sudoku grid as a 2D array, of course. If you don't know what a 2D array is, essentially, you have an array A, right? And inside that array, you have another array. Yeah, so when you print it out, right, it looks like it's a 2D plane. And it is represented like this. So array ij, what that means is the ith array, no, it means the jth element in the ith array. That's what it means. Okay, and we create two more Boolean 2D arrays for the rows and columns. Rows stores an array of 9 zeros, columns store an array of columns with 9 zeros. Zeros are just a placeholder for blank. Okay. Yes, and this is what it looks like. Okay, what about the 3x3 grids? So by doing this rows and columns, right, we can check if each row and each column has only the numbers 1 through 9 and they only appear once. But what about the 3x3 grids? The 3x3 grids are like this, the one that my mouse is hovering over. 3x3 grids like that. How do we check for those? So for those, we have to store them in a 3D array actually. And this 3D subarray can be represented again as a 2D array I and j. And they actually represent each 3x3 grid. How do they represent it? Essentially, I and j go from 0 to 2. And because the array is 0 index, that means it's a 3x3. And we can use that to check by using a set. Oh, and by the way, a set in C++ is a data structure that means that it can only have one of each element inside. So if let's say a set has 1, 2, and 3, and you try and input another 1 into this set, nothing will change. It'll still just be 1, 2, and 3. Okay, now that we have all of the elements in our Sudoku board, we can check for each one if row I value -1 equals 1, then it's used already. Otherwise, we set that row to value, we set it to 1. Y minus 1 is because all of the arrays are 1 indexed also. Okay, for the 3x3 grid, we just divide each of our indexes by 3. And if it's an invalid solution, then if it's used already, then it's an invalid solution. Like, okay, otherwise set to 1 to show that it's true. Okay, so why can we divide an integer by 3 in this case? It's because the truncation of the values actually works in our favor, since we're using an integer and not a double. You can see that actually when we're checking each grid, right, it can be proven that given the truncation of the integer value, it will always work in our favor to check whichever grid we want. Okay. And to determine the solution, we can use a set also. Or we can also just pass through each array and see if there's a unique that is filled with unique numbers. And this is the solution. Okay. I think that's that. Yeah. So does anyone have any questions? Okay. If there's no questions, then I will move on to our lesson for the day, which is data structures. So give me a second to pull that up. Oh, and on a side note, I took a look at the contest scores. I don't know how many people here were doing. I don't know how many of the people who did the contest were actually beginners, because I'm pretty sure some of the advanced people joined in on it, but Yeah, it's fine. I'm very happy to say that uh, 30 people attempted it, which is kind of good enough, if you ask me. Okay, data structures. Y'all can see it on my screen. Wait, can y'all see my screen? Just give me a thumbs up. All right. Okay, let's get into it. So, data structures, an integral part of C++. Okay, this is our agenda for today. These are just all of the data structures in C++, minus a few. Okay, firstly, we have to go through time complexity. In Informatics Olympiad, the efficiency of our code is of utmost importance. As of this point, I don't think any of the syntax questions we've given y'all will make your TLE, unless maybe you use some kind of crazy algorithm. But in in comparative programming, you'll face TLE, which means time limit exceeded, in many of the problems that you encounter, and it's going to be very frustrating. But first, we have to understand why does it TLE and how do we find out what will not TLE. So we have to understand this thing called time complexity. The time complexity is the computational complexity that describes the amount of computer time it takes to run an algorithm. Usually, we use the worst case time complexity. And if you've seen, every problem that we have has different subtasks, which gives us different limits on the problem and the inputs in order to give us like a chance in order to solve a problem with a worse time complexity than is possible, but still get some points. Okay. And time complexity is expressed as a function of the size of the input, usually used with the character n. So it uses the number of operations that our algorithm uses. So let's take a look at this. What's an operation? C in A and B. That's two operations because you're getting A and B as inputs. Those are two different operations. To C out A plus B, it's also two different operations. One operation to C out and one operation to add the numbers and one operation to see out the result. So in total, there's four operations. Okay, so what are the inputs A and B? And we let the number of operations the program needs to be at. We represent it as function A and B. Does this depend on the size of the inputs? No, it doesn't depend on the size of the inputs because the size of A and B does not change how many operations we need to do. Therefore, the number of operations in this code will always be 4, i.e. f equals 4 regardless of A and B. This is referred to as a constant. Okay, let's look at another example, the question sum int. Okay. We use one operation. One operation is getting the input n. One operation is used to input the integer x. Another operation to sum x into our variable sum. One operation to output the sum as well. So if you look at this purple box here, you'll notice that they're actually inside of a for loop. That means that these two operations are repeated n times throughout the code because they're in a for loop that runs n times. So how long does this operation take? Well, if we do the math, we see one operation here, one operation down here. Okay. Yeah. So I don't know why this one is on a different slide. We look at this formula here. There's one operation up here, one operation down here. Both of them are outside of the for loop, so that's 1 plus 1. Inside the for loop, there's two operations, and we have to do them n times. So we just do it like math, 2 times n equals 2n. And so in total, it takes 2n plus 2 operations to finish this procedure, this code. And because n is part of this formula, that means that the size of n does affect how long it does affect how long our algorithm takes. So let's look at another example, right angle triangle. One operation to input n, and we see there's two for loops called nested loops. There's one operation inside the nested loop and one operation inside the outer loop. So this operation in the nested loop is repeated I times, I referring to the outer loop's I, integer I. The other one, C out new line, is in the outer loop, and so that is repeated n times. And we see this green box to represent repeating n times also encapsulates the purple box because this purple box is a nested loop. So what's the number of operations here? Okay, if you don't understand this, essentially, we have to run this one and we have to run this one I times, and we have to run the outer loop n times. Therefore, we kind of do some nifty maths over here in order to find out that our total time complexity is half n squared plus half n. N squared is because of the nested loop. So just keep in mind, every time you have a nested loop, it's n squared time complexity. However, obviously you can see trying to find the exact number of operations is very cumbersome, and it's already an estimation. So there's not really much point as to finding out our time complexity. Not really much point as to finding the exact number of operations. And usually, runtime for small inputs is usually negligible because computers are quite fast. And so we introduce big O notation. What is big O notation? It's a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. I don't understand what that means either, but in layman terms for everyone, it just drops the constants. Constants means like 4, 5, 6, like just straight up numbers. We just drop them and we only care about the dominant terms. So what are the dominant terms? The dominant terms would be our input, and we describe it using the letter n. So if we look here, the exact number of operations for each of the questions just now, 4, 2n plus 2, and half n squared plus half n. We take the most dominant term, which is to say the one that is like the biggest, the one that would affect our computational complexity the most. So in addition, since the number is just 4, we take it to be a constant and it's just as good as being O1. Over here for sum in 2n plus 2, we don't care about the constant 2, we take 2n, and we also don't really care about the 2 in 2n, so we just take it as n because n is the most dominant term. In right angle triangle, we see half n, it has the term n inside it, but because n squared is bigger than just n on its own, therefore we just take n squared. We don't care about the half n, and we don't care about the half over here in n squared. And each of these has its own name, constant, linear, quadratic. And this is a graph. So if you look at your code, right, and you find that maybe your code is constant, all right, it has no loops, it's just constant, and it's an O1 time complexity, then that's very good. Or maybe it has log n. If it's On, which means it's linear, maybe it has one for loop. That's also pretty good. O(n log n is also quite good. O(n log n usually appears in stuff like sorting. because in C++, the sort function is actually n log n. And the worst is n factorial, because, yeah, you can figure it out, I guess. On squared is a nested loop. On cubed is three nested loops, yeah. And we don't want that. So try and minimize the number of loops and nested loops you have. Okay, let's have a surprise test. What is the big O notation of these things over here? Yeah. Can anyone give me an answer? Just unmute yourself. 2n squared plus 4n plus 1. Can anyone give me what's the big O notation?
I think that's all. That's all of m. All of n squared.
O of n squared. Wait, who was that?
Elwin.
Okay, Alwyn. Okay. I can't really reveal the answers one by one, so let's just go through all of them. What about n cubed? 6n cubed. Anyone else? We don't want to have the same person
O n
answering again.
cubed. Is it
O
O
n
n
cubed.
cubed?
Okay, O n cubed. That's a good answer. What about one? Let me count the zeros here. 100,000 n plus n to the power of 9. Wow. N to the power of 9. That's 9 nested loops. Anyone can figure out what's the big O complexity? Okay, let's just. Okay, should I pull up an RNG? Nah. Okay, I'll just pick someone. How about Matthew? Matthew, are you there? If you can't speak, you can just type it in chat. What is the big O notation of this 100,000 n plus n to the power of 9? Okay, is no one gonna give me an answer? Okay. Alright. 100,000 n plus 9 to the power of n. Actually, if we follow our logic, it's also quite simple. This one is actually pretty interesting. 2 to the power of n plus 2n factorial. Which one is the more dominant one? So if we look back at our graph, maybe we can see. Okay, so which one is the more dominant one? O(n) factorial or O2 to the power of n? Okay, I'm not gonna waste any more time. I'll just go on to the answer. So, yep, the answers given for the first and second one are correct. Good job. O 100,000 n plus n to the power of 9 is just n to the power of 9 because that's the more dominant one. Over here, 2 to the power of n plus 2n factorial. N factorial is actually the more dominant term because if we look at our graph, the O(n) factorial is steeper as compared to O2 to the power of n. So it's O(n) factorial. And 10 to the power of 100 it's a constant term because there's no n inside. Even though it's a really big number, we still take it to be a constant term, so it's O1. Okay. So how fast is fast enough? This graph, this tables over here is actually going to be really useful. You can always look back at it. Essentially what you do is you look at the question, right? How big is n or whatever character they're using? If n is 10 to the power of 7, that means that the worst complexity you can have is O(n). If it is 10 to the power of 6, then the worst complexity you can have is O(n) log n. Do note over here for a constant term, technically it's not actually infinity, but because the computers just run so fast, therefore we'll take it into infinity. Okay. The more common ones are these blue color ones, O(n), O(n) log n, and O(n) squared. Try not to have more than O(n) squared, because like if you have O(n) cubed, then the max n you can have is 500, which most problems might have as a subtask, but it's probably not going to be a very large number of points. So if you can't think of a faster algorithm, try and use O(n) squared lah. Limit yourself to that. Although, if you're trying to scam a subtask, going up to like O(n) factorial, I don't care. That's up to you. If you feel like you want to just go on to the next question, that's entirely your choice as well. Okay, but what is a log? So if you see here, n log n, right? What is log? So if you're from RI and you're in year 2, you wouldn't know what a log is. For RGS, I don't know what the syllabus is, but I'm assuming you also don't know if you're year 2. So log stands for logarithm, and it's essentially the opposite of an exponent. So an exponent is like 5 to the power of 7. 7 is the exponent. And it's just 5 times 5 times 5, 7 times. But if we reverse it over here, logarithm, log base a, which is log a, the a is base. Okay, log base a of a to the power of b is just b. I don't know how to explain this any other way, but it's quite useful to go and search it up on your own. So in CP, if you just have log, it means log base 2. In actual math, just having log means nothing. You need a base. But in CP, we just say log base 2. So that means that log 4 equals to 2 because log base 2, 4 equals to 2. Log base 2, 8 equals to 3. Log base 2, this equals to 31. Another way of seeing this is you see log base 2, right? Log base 2, 4. 2 to the power of 2 is 4. 3 to the power of 2 is 8. 31 to the power of 2 is this number. That's what log means. Okay, so now that you know about your big O notation and time complexity, let's move on to data structures. So data structures is actually more of a syntax as compared to actual techniques. It's usually not the only thing you need to know to solve the problem, unless it's a syntax problem, then yes. And it's usually used in conjunction with other techniques and algorithms. So you need to be familiar with data structures that you can exploit when thinking of solutions. Because if, let's say, you're using a data structure that doesn't suit the problem, most likely you'll need an even more complicated algorithm, or you'll just TLE. So what do I mean by this? Okay, wait. Yeah, let's look at these. So if we go back to the front page, right, you'll notice that there's actually a lot of different data structures in C++. Why? Because C++ is actually a very fast language. So all of our data structures have their own unique points. It's not like Python where we just have a list, because in Python, accessing a list is actually really, really slow. So in C++, we have data structures which have their own, unique way of being used in order to capitalize on their time complexity and how fast we can access and input values. But because of that, it also means that they are very rigid in how we can use them. So let's look at the first one, array. You all have already learned of an array. It's a series of elements of the same type, e.g. integer, boolean, string, or whatever, placed in a contiguous memory location. What does that mean? Okay, in an array operation, you can modify or get access any element at index I. This takes O1 time complexity. And the limitations of an array is that you cannot change its size after creation. So let's say you have an array that has size 5, or it has size n, and you fill it up with n number of elements. You cannot add any more elements to the array. All you can do is modify what elements are in the array, or you can access what elements are in the array. Okay, let's go. So this example here, you have an array with 5 space for 5 elements, 1, 2, 3, 4, 5. You can output the first index 1 in the array. But if you output the 100th index of the array, it will actually be a segmentation fault. Because we said array has only 5 slots, right? 1, 2, 3, 4, 5. So if you go to the 100th slot, the computer doesn't know what you're talking about because you didn't give it 100. You didn't tell it to create 100 spaces. So we call this a segmentation fault, and it'll probably give you undefined behavior. Or the computer will just, if you're using a text editor, it'll just tell you, oh, out of bounds. Okay, some side notes. All the data in your computer is stored in your RAM, random access memory. I think that's what it's called. Okay, so in an integer x, you have an integer as 8 bytes of memory, and that's known as its address. To get its address, aka its location in your computer, you can use the ampersand operator. I call it ampersand. Ampersand x gives you the address of x, also known as its pointer to x. So what does that mean? A pointer to x essentially is the address that this data has in the computer's memory. So if you ask your computer, oh, what's the value of integer x? It doesn't look in its data in its memory and it's like, oh, find integer x. No, it actually finds the address of x and it goes to that address and then it gives you the value that's at that address. So let's look at it. If we output the pointer of a, it won't output something like a equals 69. It will actually output something like this. That's its address, but we don't really have to know that. Why are we teaching this? I don't know. Okay, what is the data type of pointer x? So, uh, what is this? Oh, integer with this star. The star over here is a type of pointer to an integer. Similarly, a char character with this star thing is a type of pointer to a character. So to assign a pointer to x to a variable, you can do it this way: integer star p equals to ampersand x, or pointer to x. Now, what does the type integer star star mean? Well, it's a pointer to an integer. I don't know what that means, and I've never used it before. So honestly, just don't need to bother about it lah. Okay, your array variables are actually pointers to the first element in the array. So if let's say you have an array ARR, right? If you just see out ARR without referencing an index, it will just point to the first element in your array. It's a pointer to the first element in your array. And you can dereference it and perform any kind of operation on the data type in that first slot. So we see here, right? ARR, this address over here, this pointer actually points to the first element in the array ARR. So if you dereference it, which is the star, by the way, the star means dereference. If you dereference ARR on its own, it will just output 10 because 10 is the first element in the array. And you can perform arithmetic on it. ARR plus 2 will point to the second index ARR, the second index in ARR, which is 30. And you dereference that and it'll output 30. Okay, next up, vector. So what is a vector? A vector is a better kind of array. Currently, we have taught in the elementary class how to use arrays, but actually most people who do C++ and competitive programming would choose to use a vector instead of an array. Why? Because a vector is resizable. What does that mean? It means that you can add and remove items. So if you have an array, right, and an array can only have 5 spaces if you initialize it to have 5 spaces. If this is a vector instead, you could actually add a 6th, 7th, 8th space later on after initializing it. So that's pretty cool. And here are some operations. v.pushback means that if you have your vector, right, you add an element to the back of it, the back of the vector. It's kind of like Python appending. So you can push back the data types like 1, 2, and 3. You can also index it. It works like a normal array. 0 is the first, 1 is the second because it's 0 indexed. You can also do arithmetic on it. You can modify the values inside the vector. As I said, it's just a normal array, but better. You can also remove the last element from a vector. So if let's say a vector has the elements 1, 2, 3, 4, 5, v dot pop back essentially removes the element 5. So now it's just 1, 2, 3, 4. And you can also use this dot size function on it in order to find how many elements are inside. So let's say if your vector had 1, 2, and 3, v dot size would be 3 because there's 3 elements inside. If you're ever confused about what kind of operations you can use on a data type, you can actually just Google it. Google will have this kind. Okay, how do I say this? Yeah, you can Google it and there'll be a kind of directory which will point you to all the different kinds of operations you can do on a data type. It's quite useful. DQ. Okay, what's a DQ? Pronounced as Deki or DQ. It is a double-ended Q. I pronounce it as DQ. Essentially, it's a vector, but you can also push elements from the front. So you see here, in a vector, you can only add elements to the back and remove elements from the back. So you cannot add an element in the front. You cannot add an element like in the middle of it. You can only do it at the back. So in a DQ, it's like a vector, but you can add and remove stuff at the front as well. Okay, so let's look at the kind of operations. So it can push an element to the back. It can push an element to the front. You can see out the elements according to their indexes. It's also zero index. You can do arithmetic on the indexes, or you can modify them. You can pop the front and pop the back out. Pop just means remove it. It doesn't see out anything. It just removes it from the data structure. Okay, so time complexity comparison, memory ratio 1, 2 to 4. As you can tell, vectors, since they're like better than an array, it will use more memory. A DQ is also better than a vector, so it will use more memory. Time ratio is all the same in order to access or add elements. And functions, you can edit or query an array. Query means, let's say you want to find out what's at index 5 of an array, right? You can do that. A vector, you can add/remove elements from the back. For a DQ, you can add/remove elements from both sides. And for all of these, you can also edit/query the elements inside. Okay, next up, a pair. I used a pair when explaining a problem yesterday. So what is a pair? A pair essentially just stores two things together as one thing. Two things because it's a pair. Haha. And it is quite useful when you are storing things in an array or vector or basically any other data structure. So it stores a pair of values. Let's say you have pair integer, integer. That's how you initialize it. A. So that's a pair. A is a pair. And what does this mean? It means that the first value of the pair is an integer. The second value of the pair is also an integer. So how do you assign data in a pair? You just use dot first and dot second. Notice that there's no brackets behind it like a normal function. So a dot first equals 5 means that the first element in the pair is 5. A dot second equals 6 means the second element in the pair is 6. If you want to make a pair, okay, wait. There's another way of assigning data to a pair. You can use make underline pair 5, 6. It'll give you the same kind of values as if you use this method. But most people would rather use this curly brackets instead because it's faster to write. These curly brackets are essentially the same as make pair. Okay, use in data structures. If let's say you have a vector, when you want to initialize what's inside of a vector, oh, I should probably explain this. Yeah, give me a second. I'll just pull up my VS Code. Uh, so let me just do. Okay, let's say we want to initialize any kind of data structure other than an array. For an array, you just use the data type of it, and then its name and how many elements are going to be inside of it. That's for an array. But for other data structures like a vector, let's say I have a vector and I want it to hold integers. What you do is you have these two, the lesser than sign and greater than sign is like a bracket, and you put the data type inside. So let's say it's an int, and I give it a name vex. So that's how you would initialize this data structure. You can also give it a starting value. Let's say I want this to have 1, 2, 3. So that's how you would do it. Okay. Oh, my bad. Curly brackets. 1, 2, 3. And the same thing goes for pair. If you wanted a pair integer string, let's say, you can also do that. So good thing about pairs is that you can have different data types in each of the values. One thing you can also do is you have a data structure, right? And you, instead of having just like an integer, you actually have a pair. It holds pairs like that. So that's pretty useful. You can also, you can also initialize it. Like, it would probably look like something like cool, hello, something like that. Okay. So let's go back to the slides. Okay. Yeah, so that's why I just showed you v dot pushback make pair. That would be for your vector. Instead of using make pair, you could also use the curly brackets like just now. Next, stack. Okay, so what is a stack? It uses FILO, or first in, last out. It also uses last in, first out. So what does that mean? So, in words, what that means is that if you visualized a stack data structure like an actual stack, you can you can only add elements to the top of the stack. So we look at this diagram here, that I put 1, then 5. 5 can only go on top of the stack. 6 on top, 7 on top. In coding, this on top would refer to the back. So the back of the stack. And similarly, in a stack of books, you can only remove the books from the top. So let's say I have 1, 2, 3, 4, 5, 6, 7. 7 is the only one that can be removed. You can't remove 1 or 5 or 6 when 7 is on top. Then 6 is next. And in a stack, you can also only check what is the value of the element at the back, aka at the top. Because maybe we use the book analogy, you can only see the title of the book on top, not including if you were to look at it at the sides. That's cheating. So you can only see the value of the element at the top of the stack. But you can also count how many elements are in the stack, because if you have a stack of books, you can count how many there are. And to do that, you can use the dot size operator. You can see all here over here. Dot push will push the element to the back of the stack, aka the top of the stack. Dot pop will remove the element at the top of the stack. See out dot top would point towards the value of the element at the top of the stack, and dot size points towards the size of the stack. Okay. Yeah, stack overflow joke. Q. So this is different from DQ, because it doesn't have the double-ended over here. So it's a first in, first out, last in, first out. So what does that mean? We can view it like an actual queue. A person joins a queue. If you join the queue, you can only join at the back of the queue. And you see the 1 is gone, right? If you want to leave the queue, you can only leave from the front of the queue. Okay. So in a queue, if you use dot push, it will add the element at the back. If you use dot pop, it will remove the element at the front. You can also access the front and back of the queue. You cannot technically you can access the middle of the queue, but I don't really do that. We don't really do that. If you had to access the elements in the middle, you probably shouldn't use a queue. And yes, that's about it for queues. Oh yes, you can also check for its size, and you can also check for whether it's empty. If you use .empty on any kind of data structure, it'll return a Boolean value of true if it's empty or false if it's still got elements inside. Okay, if let's say your queue is empty and you try and .pop on it, since .pop has to remove an element but there's no element inside, it will result in a segmentation fault. So if you have any kind of RTE inside of your code, maybe you might want to check if you're trying to access or remove an element from a data structure when it's empty. Okay, priority queue. A queue but with priority. First in, first out, last in, last out. Okay, so a priority queue, it works just like a queue. You can only come in from the back and leave from the front. But what's different with this is that it is sorted. So a priority queue is sorted, and by default, the largest value is at the front of the queue. You can use a custom comparator to make it such that the queue is sorted in the other way. E.g., if the default is from smallest to largest, you can use a custom comparator to make it sorted from largest to smallest. And yeah, so we look at this. We add the element 1, and if we add the element 5, even though in a queue, wait, how is this supposed to work? Okay, so priority queue, the way you insert elements is different from a regular queue. Let's say you have the element 1, right? In a normal queue, if you add 5, the element 5, it will go to the back. But in a priority queue, since it's sorted, 5 will actually go into the front because 5 is greater than 1. Then, if you add the element 3, 3 is greater than 1, so it'll go in front of 3, but it's less than 5, so it'll stay behind 5. Then, if you want to pop an element from the queue, you can only pop the front, you can only pop from the front of the queue. You can check for the top of the queue as well. Top refers to the one at the front, which is 3. And you can also find its size using dot size. Okay. So custom comparators. One commonly used custom comparator would be this. So what this over here means is you create a priority queue. It holds an integer. It holds integer data types. You use a vector as a kind of body in order to apply this custom comparator greater int. This greater int, what it does is it reverses the order in which it's sorted. So if the priority queue originally was sorted from, let's say 5, 4, 3, 2, 1, because it's greatest to smallest, using this greater int over here, it would actually reverse it to be 1, 2, 3, 4, 5. So 1 is at the front of the queue. Okay, sets. So there's sets, multi-sets, and unordered sets. Let's look at what they are. A set is it holds elements in a sorted order. So and all elements in a set are distinct. So this is how you initialize it. Set. Let's say you want to put an integer inside, so set int s. S is the name. If let's say a set has okay, yeah. So we'll cover that later. To add an element into a set, you use dot insert 9, and it'll just insert the thing in here. If you insert another one, let's say 2, 2 will go in front of 9, not because sets are you only add to the front, but because it's sorted. So because 2 is smaller than 9, therefore it'll go to the front. 6 is greater than 2 but lesser than 9, so it'll go in the middle. And let's say you did s dot insert 6 again. The thing is, because a set only has unique elements, therefore if you inserted 6 again, the set will remain unchanged because 6 is already inside. Okay, dot find x returns an iterator to the element. So over here, if you did dot find 6, dot find 6 on S, the set S, would return you an iterator pointing towards 6, where the location of 6 within the set S. The iterator, I think it is just a pointer value. Okay. So what if you do dot find on an element that is not within the set? Well, it'll just return you s dot n because no element is found. It'll return you a pointer that points to the end of the set. So this is actually very useful. If let's say you have a set in your, okay, if your CP problem requires a set and you need to know if a certain number is inside of your set, you can use this function. You can use this, you can use if s dot find 10 not equals to s dot n in order to see if the element is inside. So let me just show you that. Okay, we are back on VS Code. Let's say I have a set, it holds integers. It's called S and it's got 1, 2, and 3 inside already. In my int main, right? If I wanted to check if, let's say, the number 10, right? If 10 is in the set S, how can I do that? I can use an if statement if s dot find 10 is, not equal to s dot n. That means that 10 is in the set S. Why does this work? Because how do I say this? S dot find, if 10 is not inside the set, it will return S dot n. That means that if S dot n is not returned, 10 has to be in the set. Because if it didn't return S dot n, that means that it returned where 10 was in the set. And if you return an address pointing to where 10 is inside of the set, that means that 10 has to be inside the set. I think that's quite intuitive. Okay, so let's go back to the slides. Okay. Okay, so you can actually also do s dot erase. What s dot erase does is it removes the element from the set. So in order to erase an element from the set, I think you have to give it a pointer towards that variable. So if you wanted to remove 6 from the set, you would use s dot find 6, pass that into s dot erase, and it will remove it from the set. Okay, extensions, multi-set. So a multi-set can have duplicates. There's also an unordered multi-set, but we usually never use it. And then an unordered set. So an unordered set is just like a normal set, but when you insert an element, it won't sort it for you. So if you insert 3, 1, 2, it'll just be 3, 1, and 2 inside the set. If it were inside the unordered set. If it was a normal set, it would automatically sort it to be 1, 2, and 3. Okay, maps. So there's map and unordered map. We don't really bother about multi-map. Maps, how maps work is there's a key to a value. In Python, it will be known as a dictionary, and it maintains the keys in a sorted order, similar to a set. And this is how it works. So you have how to initialize it. It works like a pair. You have the data type of the key and the data type of the value of the key. So it would look like this if it was just 2 integers. So what does that mean? How would you assign values in a map? What you do is you have map square brackets here. Inside the square brackets is the key value. And you assign the value to the, okay, what's inside the square brackets is the key. And you assign the key a value of 1. That means that later on, if you say what is the value to the key 1029, it would output 1. You can do it for anything. If let's say your key value type was a string, as in map string comma integer, then over here instead of 1029, you would probably have a string like hello equals 1. Okay. Unordered map is essentially a map but not ordered. It's like an unordered set. It's slightly faster. So if you don't need to have your map be in order, then just use an unordered map. It'll make your code faster. If I remember correctly, our diagnostic test for splitting into a beginner and advanced, if you used a normal map, then you would TLE on one of the questions, which is Yale University. But if you use an unordered map, then you wouldn't TLE. Okay, list. So lists in C++, it's the same as like Python. You can insert an element anywhere inside the list and delete any element anywhere inside the list. It's very powerful, right? Because in a normal array, every single data structure in C++, it has some kind of drawback. But if you look at a list, it looks like it has like it's so much better than any different data structure, right? But why doesn't anyone use this? Actually, we don't use it because it's very slow. So if let's say you have a list 1, 2, 3, 4, 5, 6, all the way to 10. If you wanted to access an element inside of the list, it would actually take O(n) time complexity. And it would also take O1 to delete and insert an element anywhere inside of the list, only if you have reference to the element, meaning that you know exactly where the element is already. But if you did, then if you had to do that, if you had to know where the element was inside of the list before you can access it or delete it or insert it, then you probably won't be able to solve a lot of the comparative programming questions. So TLDR, a list is very slow and it kind of sucks, so don't use it. Okay. Yeah, we won't go through how to use a list. And these are the problems that we have for y'all to go through. Okay. I think there's solutions for them in the slides, but for now, how about we just go through them? The ones with stars are the ones that we have solutions for. So you should probably do those first. If you've already done it, then you can do the ones that don't have stars. But for now, yeah, just do these problems. I'll type it into the chat.